You ever wonder how engineers can actually predict and, even control the insane chaos of a car crash? It's not magic, not at all. It's physics. And today, we're going to see how the pretty elegant science of energy can help us understand exactly what happens when a couple thousand pounds of moving steel meets something that isn't moving at all. All right, let's get into it. So here's our game plan. We're going to start with our spring-loaded problem, then do a little dance with the types of energy involved. After that, we'll look at what happens when forces decide to break the rules, find the one equation that governs everything, and then, finally, we'll solve the crash. Okay, so to get us started, auto manufacturers run simulations like this all the time to test their safety designs. We're going to look at a classic version of this scenario, a car hitting a huge, high-tech spring that's designed to absorb all that impact. So this is our big question. We've got a 1,000-kilogram car that's about the weight of a small sedan, and it's moving at 15 kilometers per hour. Now, that's not exactly highway speed, but believe me, it is packing a punch. The question is, how far is it going to squish this massive spring? To figure that out, we actually need to step back a bit and talk about energy. All right, let's start in a perfect, simplified world. A world where there's no air resistance, no friction, nothing messy. In this perfect little bubble, the story of our crash is really just a beautiful dance between two types of energy. First up is kinetic energy. And this one's super easy. If something is moving, it has kinetic energy. The faster it goes, and the heavier it is, the more kinetic energy it's packing. Our car, right before it slams into that spring, is just a rolling bundle of pure kinetic energy. The dance partner for kinetic energy is potential energy, which is really just stored up energy. Think of a drawn bowstring or a roller coaster sitting at the very top of a hill, just waiting. In our crash, as the car squishes the spring, its kinetic energy doesn't just disappear. Nope, it gets converted and stored right inside that spring as potential energy. This image here shows that energy transfer perfectly. See, on the left, the block is just sitting there, no energy. But stretch it or compress it, and bam, you're loading it up with potential energy. The second you let go, all that stored energy turns right back into the kinetic energy of motion. It's a perfect, seamless swap. And this points to a fundamental law of the universe, the conservation of energy. In a perfect system, energy is never really lost. It just changes its costume. It goes from kinetic to potential and right back again. The forces that let this happen, like the force in our spring, are what physicists call conservative forces. The total energy always stays the same. But yeah, as we all know, we don't live in a perfect, frictionless world, do we? There's a spoiler in our story. There's a force that doesn't play by these nice, clean rules of conservation. And that force is friction. So here's the crucial difference. A conservative force, like our spring, is kind of like borrowing money. You store the energy, and it gives every single bit of it back. But a non-conservative force like friction, that's more like paying a service fee. Every time it acts, a little bit of your energy is permanently taken out of the system, usually as heat. It's spent. You can't get it back. And that is the key. Friction always works against motion. So as our car is compressing that spring, the friction from the road and the tires is actively fighting it, stealing some of that precious kinetic energy and turning it into heat before the spring even gets a chance to store it. So how in the world do we account for this energy thief? It kind of seems like our simple, neat idea of energy conservation is broken. Well, thankfully, physics has a more powerful, more universal rule that can handle everything, including messy forces like friction. It's called the work energy theorem, and you can think of it as the master bookkeeper for all energy transactions. It basically says that if you add up all the work done on an object, both by the forces giving energy and the forces taking it away, that grand total will exactly equal how much the object's kinetic energy changed. And this puts it perfectly. The change in the total energy of our system is exactly equal to the work that those non-conservative forces, like friction, did. Think of it this way. The work done by friction is just an energy withdrawal. The energy isn't gone from the universe, it just got siphoned off as heat. And now, finally, we can account for every single last bit of it. Okay, armed with our universal energy equation, let's go back to that car crash. We are no longer in a perfect, ideal world. We are in the real world with real friction. Let's solve this thing. So here's our plan of attack. First, we'll calculate the car's total kinetic energy right at the start. Then, using our new theorem, we're going to subtract the energy that friction steals away during the compression. Whatever energy is left over, that's what the spring actually gets to absorb, and from there, we can figure out exactly how much it compresses. So first, let's look at that ideal world answer again, the one with no friction. If every single joule of that car's kinetic energy went straight into the spring, it would compress a maximum of 2.8 meters. Remember that number. That's our baseline. But now, let's bring friction into the mix. With a pretty typical coefficient of friction for tires on dry road, the spring only compresses 1.95 meters. Wow, that is a huge difference. I mean, this bar chart just says it all, doesn't it? Just look at that gap. Friction, all by itself, prevented almost a full meter of compression just by turning a huge chunk of that kinetic energy into plain old heat. So in a weird way, friction actually helped the spring stop the car. Which brings us to a final really interesting thought. We called friction an energy thief, but in our crash, it was actually kind of a hero. This idea of deliberately wasting kinetic energy is the entire principle behind car safety features like your brakes or the crumple zones on the front of your car. They are non-conservative systems specifically designed to dissipate energy, to turn a violent impact into manageable heat and mangled metal. So the real question is, how else can we harness these energy-wasting forces to make our world even safer?